The principle of stationary action. What is it? All physical problems usually involve finding one or more physical quantities as functions of one or more background physical quantities. We consider a general problem, finding the etas which vary over the size. We shall abbreviate it like this, with indices alpha and I running over values to cover all the etas and size respectively. As specific examples, we will look at the position as a function of time for a particle moving under some external potential, as well as the electrostatic potential as a function of position for a certain given charge distribution. Only two dimensions of space are shown for clarity. Now, it turns out that the laws of physics governing the etas can be encoded as a function of the etas, the first derivatives of the etas over the size, and the size themselves. This function is called the Lagrangian. For example, the Lagrangian for a particle is given by the kinetic energy minus the potential energy, and the Lagrangian for the electrostatic potential is given by the energy density of the electric field minus the potential energy of the charge distribution. Now, how does the Lagrangian encode the laws of physics? Here is where the principle of stationary action comes into play. Take an interval in the space of the size. For the motion of a particle, it would be a time interval. For the variation of potential, it would be a region in space. The interval may be infinite if need be. Now, let us say that the values of the etas are known on the boundary. These may be known by direct observation, like the position of the particle at the start and end time. In the case of the electrostatic potential, it is preferable to take the region to be all of space, infinite, and we know that we can choose that the potential go to 0 at the boundary. Now, inside the region, we consider all possible configurations of etas satisfying the boundary conditions. Thus, for the case of the particle, we consider all possible paths it could have taken between the known start and end points. For the electrostatic potential, we consider all possible field configurations satisfying the boundary conditions. We now define the action, denoted by S, for a specific configuration of the etas as the integral of the Lagrangian over all the size covering the region. For the motion of a particle, the action for a path is defined as the integral of the Lagrangian over time. For the electrostatic field, the action for a given potential field is defined as the integral of the Lagrangian over space. Now, we use the principle of stationary action, which states that the real configuration of the etas are such that the action takes a stationary value. That means that making a small change in the etas will, up to first order in the change, have no effect on the action. Now, it may seem impossible to find the action for so many paths and check how it behaves for small perturbations. However, one can show that the configuration with stationary action is one which satisfies a simple equation called the Euler-Lagrange equation. This is the Euler-Lagrange equation. There is one such generally second order partial differential equation per value of alpha. For the motion of a particle, this equation gives Newton's law. For the electrostatic potential, this equation gives Gauss' law. And so, we wanted to find the etas as a function of the size given a Lagrangian. We did it by the principle of stationary action and found that the resulting Euler-Lagrange equations gives the configuration of the etas. Thank you for watching.